So, hi everyone, and welcome to today's edition of our Extreme and Probabilistic webinar. Before we start with the talk, let me go through the usual technical stuff. The slides which our speaker will be using are on the seminar webpage, so you may open it in parallel in case you want to look up some definition or something. If you have any questions, then please either do unmute yourself and just ask the question, or write it in the chat, and then we will notify the speaker. Also, there will be, of course, time for questions at the end. We always have a recorded part of this question session. And then we have a sort of open discussion, which is not recorded. So that's where you are free to say anything. And so now I think we can begin with John Noel, who recently moved to University of Victoria, and John will be talking about common graphs. So please.
Thanks, Jan, for the introduction, and thanks to you and the organizers for the invitation. And thanks for putting on this very nice webinar. It's been nice for you to provide such great talks during the COVID-19 pandemic. So I'm going to talk about non-bipartite K-common graphs, and this is based on joint work with Daniel Kráľ, Sergey Norin, Volec and Fan Wei. Okay, so let me. Okay, yeah, so I've got the slides on my webpage, but also Jan Volec has put a link in the chat to the, so they're also on the webinar webpage. Okay, so let's start with just a nice little warm up. So here's something which I guess most of us are probably familiar with. So if you take a complete graph on 6 vertices, you color each edge red or blue, then no matter how you do it, you must get you must get a monochromatic triangle, meaning a triangle where all of the edges are red or all of the edges are blue. And if you've never seen this before, then, well, this picture in the top right corner is essentially the proof, just a pigeonhole principle argument. And if you have seen this before, then you'll know that this is kind of the starting point when you learn about Ramsey's theorem. So in general, what Ramsey's theorem says is that for every graph H and for every integer k at least 2, there exists an n such that no matter how you color the edges of kn with k colors, there's always a monochromatic copy of H. So that is a copy of H where every edge has the same color. Okay, and of course, given that such an n exists, there's always a minimum such n, which we call the Ramsey number, and denote it by Rk of H. And I just want to make a distinction from the beginning, that just so I don't confuse anyone, that this talk is not going to be about computing Ramsey numbers, which is a very classical and very interesting problem in combinatorics. But instead, we're going to look at a sort of closely related question, which is kind of a quantitative kind of asymptotic question. So the real focus of this talk is going to be on the following type of question. So suppose that n is much larger than the Ramsey number, much larger than this Rk of H. When I say much larger, really what I mean is that you should think of n going to infinity, and we want to prove asymptotic results. So n is very, very large, and we want to know, so we color the edges of kn with k colors. By Ramsey's theorem, you know that there must be at least one monochromatic copy of H, and we want to know how many must there be. So how many monochromatic copies must you have in a coloring of a large complete graph? Okay. Any questions about this so far? Okay. If not, let's just think about the first kind of interesting, interesting case of triangles. So this is a famous old result of Goodman, which says that if you take complete graph on n vertices, color the edges red and blue, no matter how you color it, the number of monochromatic triangles must be at least this quantity here, which is basically a quarter times n choose 3 minus some small order term. Okay, and how do you interpret this? Well, n choose 3 is the total number of possible triangles, right? That's the total number of triangles in Kn. It's just the number of ways to choose 3 vertices. And this says that basically a quarter of those triangles minus, a proportion 1/4 minus epsilon. And, this is of course asymptotic as n goes to infinity. It's going to 0. So basically a quarter of your triangles have to be either fully red or fully blue. And of course this is tight. So one way to prove it's tight is to just take a random coloring. Right? If you color the edges randomly, well, I mean, if you have a given triangle, what's the probability that it's all red? Well, if we color the edges independently red or blue with probability 1/2, then the probability a given triangle is red is 1/8. The probability it's blue is 1/8. And so in expectation, you have this many, which is a quarter n choose 3 monochromatic triangles. And this is going to be, concentrated and all of that. So basically almost every coloring is going to be a tight example. So the philosophy here then that you should take away from this is that random colorings are sometimes very good for, well, avoiding monochromatic patterns. But so in this setting, we can't fully avoid them. But when you can't avoid monochromatic patterns, random colorings are still quite good for minimizing the frequency of monochromatic patterns. So in particular here, if your pattern is a triangle and you have 2 colors, then random colorings are very good. But I want to kind of caution you here that this random coloring is not the only type of tight example. So there's another nice tight construction that you get by just taking your vertices, splitting them into 2 equal size parts. So 2 sets of size n over 2, let's just assume n is even, coloring all of the edges between the parts with blue, and then coloring all of the edges inside of each part with red. Right, and this is going to give you a tight example, but it has a kind of different character to it. So here you have 0 blue triangles, and the number of red triangles is, well, if I pick 3 vertices at random, the probability that they're all on the left is 1/8. The probability they're all on the right is 1/8, and that's the only way you can make a monochromatic triangle. So you have, 1/8 plus 1/8 is a quarter. You have approximately a quarter n choose 3 red triangles up to small order terms. Okay, so this is a sort of thing that's going to come up later in the talk, that you have this kind of dichotomy between, you color the edges. You might, in some cases, you might want to find the copies equitably among the colors. So for example, in the random coloring, we found just as many red copies as we found blue copies, but you have to also deal with this situation where, one of the colors you might have 0 copies, like here we have 0 blue triangles, and when that happens, you need to compensate in the other colors. That's a kind of key idea. Okay, so let's kind of keep going with that philosophy of random colorings being pretty good. And by the way, that the philosophy that random colorings are good for avoiding monochromatic patterns, that's something that actually goes back quite far to one of the first applications of the probabilistic method by Erdős in 1947, where he proved the diagonal lower bound on, the exponential lower bound on diagonal Ramsey numbers by just taking a random coloring. So it seems that Erdős probably liked this kind of philosophy, and because in 1962 he conjectured that for any m, at least 3, the number of monochromatic copies of Km in any 2 coloring of the edges of Kn, he conjectured is at least this quantity here, which, so how do you interpret this? Again, so n choose m is the number of possible Kms. If you colored randomly, then red and blue, then you would well, each copy would be red with this probability or blue with this probability, and 2 is the number of colors. So this is just the expected number of copies in a random coloring. Okay, and of course this is true for m equals 3 because that was Goodman's result. It turns out that this is false though, in general. So Thomason in 1989 proved that the following, so there's some constant c which is less than 1/32, where 32 comes from this, this coefficient here, or this constant factor, in the case m equals 4, so 2 times a half to the 4 choose 2. So there's some constant less than 1/32, and there exists a 2 coloring of Kn, the edges of Kn, with at most c times n choose 4 copies. And when I say copies, I always mean monochromatic. Okay, so this turns out to be false. So what's the message here? Well, the message is, even if random colorings are sometimes a good way of avoiding monochromatic patterns, they're not always the best way. So sometimes by coming up with a clever constructive coloring, you can do better than a random one. But despite that, it's still an interesting question, I think, to understand the kind of role of random colorings in these problems. So, you know, try to extend Goodman's result to, you know, try to understand which classes of graphs have that property. So for which patterns, or in other words, for which graphs H, is it the case that random colorings are the best for minimizing monochromatic copies of H? So that's the question. And as we saw with Goodman's result, so if you're dealing with K3 and you have 2 colors, then random colorings are the best. And Thomason proved if you have K4 and you have 2 colors, there's a coloring that's better than a random coloring. Okay, at this point, are there any questions? Because things are going to get a little bit more technical from here, so it'd be good to ask now. Okay, so if not, let me make this all a bit more rigorous. So one thing I have to kind of address here is, what do I mean by a copy? So, you know, in the case of when we're counting cliques, it's kind of clear what a copy is, you know, of a triangle. But when you have another type of graph, we have to kind of think about, are we talking about labeled copies, unlabeled copies, and so on. So the way I'm going to measure the number of copies of a graph in another graph is in terms of the so-called homomorphism density. So this is a sort of a way of measuring how frequently a graph appears in another one. So we've got a question: what is the best known lower bound for the number of monochromatic K4s? This is I don't know what the number is, but this is a very interesting question. The number of monochromatic copies of K4 and a coloring of Kn. So nobody knows what the minimum is, but there are some existing bounds. I can't give you the references off the top of my head, but you should see, we have the references in the paper. But that is a very good question, very interesting problem. Okay, so how do we measure the number of copies of a graph in another graph? So we're do this by the homomorphism density. So the homomorphism density of H and G, denoted by THG, is just the probability that a random function from the vertices of H to the vertices of G preserves edges. What do I mean by preserving edges? I mean that if UV is adjacent or is an adjacent pair in H, they must map to an adjacent pair in G. And this kind of edge preserving function definition is also known as a homomorphism. Okay, so the picture is as follows. So you have an adjacent pair in H. We look at where they map to in F, and for every adjacent pair, they must map to an adjacent pair of vertices in G. And this sort of gives us a way of counting copies of H and G. It's not exactly what you might think of as copies, because these homomorphisms, these edge preserving functions, might not be injective. But it turns out to be a convenient notion for this type of problem. So the homomorphism density gives you a number between 0 and 1. It's a probability where it sort of measures the frequency of H and G. Just a couple of examples to get used to this concept. So if H is K2, so what is the density of K2 in G? So I define this as a probability, right? But of course, everything here is discrete. So a probability is just kind of counting. So it's just the number of edge preserving functions divided by the total number of functions. So if you have a graph G, every edge of G kind of provides two edge preserving functions from K2 to G by mapping this way or that way, right? Mapping to the endpoints in either kind of orientation. And every non-edge contributes 0. So this is your K2 density, which we also call the edge density often. And K3 would be similar. So it's 6 times the number of triangles divided by the number of vertices cubed. Okay. So here's the kind of key definition of the talk. So a graph H is said to be K-common. Well, so remember, we're talking about colorings of the edges, and we want to know if the random coloring is the best one for minimizing. So that's what I want to convey here, but it's just a little bit technical because, well, just to make it precise. So the graphs, we have these graphs G1 up to GK. We think of this, the edges of GI are of color I. And the union of these, the edge sets of the GI graphs for I equals 1 to K, are union to the edge set of Kn. Okay. And so think of this as a coloring of Kn. And we want to count the number of monochromatic copies of H. How do we do that? Like I said, we're doing that in terms of the homomorphism density. So this is just the sum over all of the colors of the number of copies of H, where all the edges have that color, essentially. That's at least how you should think of this. So sum overall I of the density of H and GI. And we want this to be at least as large as in a random coloring. And in a random coloring, so this right-hand side is the expected value of the left-hand side in a random coloring. Meaning, if these graphs GI were produced by flipping a coin, well, not a coin exactly, but for every edge picking one of the K colors uniformly at random, independently of the other edges. Okay. Are there any questions about this before I move on? Okay. So just to kind of drive this home and connect it to the previous examples. So under this definition that I've written here, the graph K3 would be too common, and that's because of Goodman's bound. However, the graph K4 is not, and that's because of Thomason's result. Okay. So we want to understand these K-common graphs effectively. One thing, so I want to tell you about the history, but one thing to address first is the fact that bipartite graphs have a sort of special status in this problem. So one thing which is kind of ubiquitous in extremal combinatorics or extremal graph theory is the fact that bipartite graphs are really hard to avoid. Okay, and one example is the Erder-Stone-Simonovitz theorem, right? If you have any positive edge density in a graph, and as n goes to infinity, if the number of vertices is large, you can't avoid, you're going to see copies of any bipartite graph. So it's really hard to avoid bipartite graphs. And one thing which really kind of a very beautiful conjecture that kind of encapsulates this philosophy, well, in kind of a strong form, is due to Sidorenko. So Sidorenko's conjecture says that if H is any bipartite graph, then for any graph G, the homomorphism density of H and G is at least the edge density, so K2 density, raised to the number of edges of H, which is, so this right-hand side is just the expected number, the expected, ooh, that's terrible. That's supposed to be an E. The expected value of THG basically in a random graph of edge density TK2G, right, with a large number of vertices, I guess. Okay. So this says that basically, if you have any bipartite graph, the number of copies should be at least as large as a random one in a random graph. I mean, from this, we can get that any graph that satisfies Sidorenko's conjecture is automatically k-common for every value of k simultaneously. So here's the proof. It's just a simple convexity argument. So if H satisfies Sidorenko's conjecture, we start with the number of, so remember GI is a coloring of the complete graph. We start with this number of monochromatic copies written as this sum, applies the bound in Sidorenko's conjecture to each summand. And then we just apply convexity. And so a key thing here is that, so remember the GI, these graphs GI, their edge sets union to the complete graph. So if I add up their edge densities, it must be 1 minus little o1. Okay. It's technically not 1, but it will be, you know, very close to 1 as n goes to infinity. And by convexity, this sum here is minimized when all of the values of the edge densities are roughly equal. And when they're roughly equal, the lower bound you get is like this. Okay, which is exactly what we wanted in to prove that it's k-common. Okay, so the message here is any bipartite graph that satisfies Sidorenko's conjecture is k-common, and Sidorenko conjectured that all bipartite graphs satisfy his conjecture. Okay, so let's now talk a little bit more about the history of these k-common graphs in the case of two colors. So k is equal to 2. So graphs which are known to be too common, these include, well, as I said, bipartite graphs that satisfy Sidorenko's conjecture. You also have the complete graph on 3 vertices, which I've already mentioned. Sidorenko generalized this to all odd cycles in 1989. And then in 1996, Sidorenko came up with a lot of other different examples of too common graphs. And these include things called triangle vertex trees, which is what you get from a bunch of triangles. If you glue together triangles in a tree-like fashion, where all the gluing points are on single vertices. So something like this is a triangle tree, a triangle vertex tree, I should say. You have triangle edge trees, which is the same idea, except you glue in a tree-like fashion on edges. Even wheels, which is an even cycle with a vertex, an extra vertex joined to everything. And more general than even wheels, he actually proved this for any graph satisfying Sidorenko's conjecture if you add a vertex joined to all of the other vertices. So that includes the case of odd wheels, because even cycles are Sidorenko. This is a very good question by Alexei. So Alexei asks if Sidorenko's conjecture is equivalent to showing that all bipartite graphs are too common. I would say not. It's not obviously equivalent, and it possibly isn't equivalent. So it's not known. Yeah, but at the moment, there's no known examples of a too common bipartite graph that's not known to be Sidorenko. So that is an interesting question to just find such an example. Okay, I'll mention now a very recent result, which I believe is maybe not on arXiv yet. Last time I checked, this is a paper of Jeszek, Lee, Leditsky, and Volec. So they extended some of these examples of Sidorenko to things like triangle trees, which is a kind of mixture of a triangle vertex tree and triangle edge tree. So you're allowed to glue on edges or vertices. Probably the simplest example is this graph here, which they call a fish. So this was, all of this was mentioned in Jun Hyung's talk in this webinar a couple of months ago. I hope I'm quoting these correctly. So I believe, so they also prove it for the octahedron, which is K222, complete tripartite graph with parts of size 2, and more generally for KABC, where A plus B is at most 7. But Yan can correct me if I'm wrong on quoting this. On the other side, so I'm going to come back to 2 common graphs in a second, but let's think about the other side. So graphs which are not 2 common. So one example is a triangle with a pendant edge. So this was proved by Sidorenko in 1989. And actually, this example was the very first example of a known example of a non-2 common graph. And this disproved a conjecture of Burr and Rosta. So the Burr and Rosta conjecture would have implied that every graph is 2 common. And so Sidorenko disproved that. Right, so also I've mentioned that Km is not 2 common for M at least 4. I just mentioned the case of K4, but this is true as well. And this is, like I said, due to Thomason. Then this was extended quite substantially by Jagger, Šťovíček, and Thomason to any graph that contains a K4. And also another interesting, so another interesting thing that they proved, so in the same paper, is that if you take any non-bipartite graph and you glue to it a very large tree, where the size of the tree depends on the graph you're gluing it to. So if the tree is sufficiently large, then the graph that you get from that is not 2 common. Again, it doesn't matter which tree you add. So it can be a path, it can be a star, it can be something in between, it doesn't matter. So graphs kind of looking like this one in the corner. And this is going to be coming up again later as well, that if the kind of issue with this graph is that it's not bipartite, and simultaneously it's quite sparse. In terms of the ratio of the number of edges to the number of vertices, as the tree gets larger and larger, this ratio tends to 1. And that turns out to be a problem for proving a graph is common. Okay, one thing I want to point out here, so on the positive side, an interesting question is just to come up with complicated examples of common graphs, or 2 common graphs. And one kind of way of saying if a graph is complicated is to say perhaps it has high chromatic number. So here we've got chromatic number 2, bipartite graphs, and here we've got chromatic number 3. Here we've got a range of chromatic numbers on the negative side, chromatic number 3, 4, but it can be very high. But you can see on the positive side, the examples I've mentioned so far, you've only got chromatic number 2 or 3. And actually, to this day, I believe the only example known to be 2 common and have chromatic number at least 4 is the 5-wheel. So this is a result of Hatami, Hladký, Kráľ, Norin, and Razborov. So the 5-wheel is a 5-cycle with an extra vertex joined to everything. And yeah, so it's a very interesting kind of outstanding problem to understand, can you have 2 common graphs of high chromatic number? And I think we suspect that you can, but proving that a graph is 2 common turns out to be quite tricky. Any questions about this history? So if not, let's move on to the quite brief history of graphs which are K common for K at least 3. So one kind of nice observation of Jagger, Šťovíček, and Thomason is that if a graph fails to be K common for some K, then it also fails to be K plus 1 common. Okay, so it's harder for a graph to be K common if the number of colors K is larger. Okay, and just kind of so this implies then that the set of all K common graphs is therefore a subset of the set of all k common graphs. Okay, so it's a sort of more, when you have more colors, it's a restricted family of graphs. To illustrate that this inclusion is actually strict, well, that it can be strict for certain values of k, let me tell you that the graph K3 is not 3 common. So remember, Goodman proved it's 2 common, but I'm going to tell you it's not 3 common. And the example is pretty simple. So all I do is I take a large complete graph, split the vertices into 5 equal size sets, color the edges between consecutive sets with red, and color all of the other edges between sets with blue. And of course, I haven't colored all the edges yet because this is a large graph. These bins have more than one vertex. And all I do is I take all of the edges inside of each of these sets and I color them green. Okay. And how many monochromatic triangles do you have? Well, you don't have any red ones and you don't have any blue ones. So you only have green ones. And how many green ones do you have? Well, think about the probability. If I choose 3 vertices, what's the probability they land in the same bin? It's 5 times 1/5 cubed, which is like very clearly smaller than 3 times 1/3 cubed, which is the density you would want to have if the graph was 3 common, if triangle was 3 common. Okay, so this is just blowing up the kind of standard Ramsey graph for triangles. Actually, an interesting side note that this construction is actually optimal in terms of minimizing the number of triangles in a 3-edge coloring. This was proved by Cummings. I'll just say Cummings et al. It's a kind of long list of co-authors. Apologies for me for not naming them all. And that was in 2013. Sorry. And so here I said that the triangle is not 3 common. An interesting extension of this proved by Cummings and Young is that actually, if you have any graph that has a triangle, it automatically fails to be 3 common. And remember, by this observation of Jagger, Šťovíček and Thomason at the top of the slide, if you fail to be 3 common, then you fail to be 4 common, 5 common, etc. So triangles are bad. They automatically make you not 3 common. And actually, up until this point, the only graphs which are known to be k-common for any k at least 3 were bipartite graphs that satisfy Sidorenko's conjecture, which I told you why they were k-common a bit earlier. So these were the only known examples. So our result then that I want to talk about in the rest of the talk, for most of the talk, joint with Daniel Kráľ, Sergey Norin, Volec and Fan Wei, is that for every k at least 3, there exists a connected non-bipartite k-common graph. Okay, and so these are the first examples of k-common graphs which are not just bipartite graphs satisfying the Sidorenko's conjecture, and in particular, they're not bipartite. Okay, and we worked a little bit harder to get this connected condition because it felt a bit more natural to have a graph which is connected than a disconnected graph. Okay, any questions at this point?
Is it clear, or could you have a graph which would be k-common for every k and not bipartite?
Ah, that's another very good question. That I'll save that one because that's going to be addressed later. But that's a very good question. Yeah, thank you. Okay. Any other questions? Okay. So let me tell you what our example looks like. So this is slightly cumbersome notation, but the definition here is hopefully not that hard to understand. So let k sub 2a, 2b, c5 be the graph that you get from complete bipartite graph with parts of size 2a and 2b by taking b disjoint 5 cycles and kind of gluing them onto b of the vertices in the set which has size 2b, the part that has size 2b. So for example, this is the case where A is 2 and B is 3. So you have 4 vertices, 2A equals 4 vertices on one side, 2B, 6 vertices on the other side. And then on half of the vertices on the right-hand side, you glue a 5 cycle. Again, this is clearly not bipartite. And we want to prove that this graph, well, essentially this graph, so this graph where A equals B equals N, so the graph K 2N 2N C5 for large N, we want to prove is, so N large with respect to K, we want to prove that that is K common. Now, before I start telling you, an overview of how the proof works, let me just kind of mention a few kind of key properties, which is kind of led us to this construction, I guess. So one is that one important thing in this construction is that the girth is even. Girth meaning the length of the shortest cycle. And in particular, it doesn't have any triangles, right? We know that if we had a triangle, we'd be dead, right? Cummings and Young proved that if you have a triangle, you're not 3 common, therefore you can't be K common for any K at least 3. So it's good that we don't have any triangles, and it's even better, it turns out, that we have an even girth. And it also helps that we have tons of 4 cycles, because when you have if you imagine one of your color classes, one of the graphs, if it's quite far from being quasi-random, that, as it turns out, boosts the number of 4 cycles substantially. And we can kind of quantify that. And that can sometimes help to find this graph. Another thing that connects back to Jagger, Šťovíček, and Thomason's examples before is that this graph is very dense. Remember, I mentioned that part of the problem with this, if you take a non-bipartite graph and add a tree, is that the graph gets very sparse in terms of the edges divided by the number of vertices. But this graph doesn't have that problem because you have quadratically many edges, and linearly many vertices in terms of n. Right, so as n gets bigger, the number of edges compared to the number of vertices gets very big. And we're going to see a little bit of how that comes into play. Okay, so let's talk kind of at a high level about how the proof works. So as usual, I've got my graphs G1 up to GK, which we think of as K different colors. And then I'm going to have an extra graph GK plus 1. Okay, and this is kind of useful for induction. So think of GI as being the edges of color I, and think of GK plus 1. So that's for I up from 1 to K, and think of GK plus 1 as being a sparse graph of uncolored edges. And that's going to be useful for applying induction. So, and the induction is going to be on the number of colors. So induction on K. Okay. And so what we prove is that, so we're looking for the number of monochromatic copies of this graph in the K colors. We'd love to say that this is at least K times 1 over K to the number of edges. That's not going to be possible though, because we have these uncolored edges. They're going to prevent that. But we can prove a bound which is in terms of how many uncolored edges we have. So we want to prove that it's the number of monochromatic copies is at least this quantity over here, where this thing in the exponent is just the number of edges in this graph. Okay, and of course, so if there are no uncolored edges, then this TK2 GK plus 1 is 0, in which case we just get the bound that we want. Right? Okay, so let's divide the proof into 2 cases. Okay, so the first case I want to consider is where, so one of the color classes, so the ith color, let's say, has a large sparse set. So what do I mean by that? So there's a linear set of vertices. So a set of vertices S, which has size at least delta naught n. And there's various parameters in this proof, and they all kind of depend on each other and k in different ways. So let's not get into details about the dependence on the parameters because we'll go a bit crazy. But let's just say, just imagine you have a linear set of vertices, so it has size at least delta naught n, where if I look at how many edges of GI land in that set S, it's a lot smaller than in a random coloring. So the number of edges in S of color I is at most P naught, S choose 2, where P naught is much less than 1 over K. And in fact, it's going to be small enough. It has to be small enough so that I can apply some inductive argument, but we'll see that in a second. Okay, then basically this GI has a large sparse set, and I want to basically ignore color I because we can't really, I mean, imagine GI could be just a bipartite graph, and we're not going to find any, if GI was just a bipartite graph, we wouldn't find any copies in GI. So essentially at this point, we're just going to give up on color I. Okay, and we're going to try to find lots of copies in the other k-1 colors to compensate for the loss of color I. And we're actually going to find all of those copies inside of S. Okay, so we remember we had this set of uncolored edges GK plus 1. So now we're going to kind of zoom in on the set S, and we're going to view the colors of GI as also being uncolored. So they kind of get incorporated into the uncolored set. So how many copies do we find? Well, so I claim that we get a bound sort of like this, as long as the parameters are done correct, are kind of chosen correctly, which is, again, like I said, a bit technical. But so where does this come from? So we get this factor in front of delta naught to the 8n. 8n is just the number of vertices in this graph here. And that's just the probability that all of the vertices land in the set S, right? And then given that they all land in S, we can just apply induction inside of S, where we get the number of, monochromatic copies then depends on how many, well, it's k-1 times this thing, which depends on the number of uncolored edges. How many uncolored edges, or what's the density of the uncolored edges? It's P naught, and that's the contribution from GI. Remember, we're assuming that they're not colored when we're counting inside of S. And this is the contribution we get from GK plus 1. And this is sort of, this delta naught, 1 over delta naught squared is kind of the worst case scenario, that maybe all of your uncolored edges sat inside of S, and you would have that many in there. Okay, and now the key thing is that here we've got this delta naught to the 8n, which is kind of hurting us. But the fact that, the fact that 1 over k-1 is bigger than 1 over k, and the fact that this exponent here is quadratic in n, whereas this one is linear in n. So this exponent being the number of edges of the graph, that one being the number of vertices. The fact that the ratio of vertices over edges goes to infinity means that for n sufficiently large, we've got the bound that we want. Okay, so this is the case where you have a large sparse set in some color. Any questions about that? Sorry if it gets a bit technical, but I thought I should tell you something about the proof. Okay, let's go to the other case. So let's assume that none of these graphs GI has a large sparse set. Now, what we're going to do, well, we're not going to throw away any colors. We're basically we're going to try to find a large number of copies in every single color. So for every I from 1 to k, where the number of copies we're trying to find is, the kind of the appropriate number compared to the edge density of that graph. So the edge density raised, again, remember that this is the number of edges in this graph. Okay. So we're trying to find these copies equitably among the colors, essentially. So one case is, so look at each individual color now. Just look at the color I, and maybe it's, so what we want to kind of answer is GI quasi-random or not? If GI is not quasi-random, I mean, there's lots of different ways of quantifying what it means to be quasi-random. But one way to quantify it is that it has a large, if it's not quasi-random, it has a large count of 4 cycles, a large 4-cycle density compared to a random graph. So if you have a large number of 4 cycles, just using a simple Cauchy-Schwarz argument, you can get a lot of copies of K 2n 2n, right? Just by, where the, basically this kind of large number of 4 cycles amplifies when you deal with a bigger complete bipartite graph. And here's the sort of vague intuition about how to deal with this case, is that most of these K2n 2n's should be attached to a fairly large number of 4 cycles, or sorry, 5 cycles. I mean, most of the vertices in most of these K2n 2n's. And why is that the case? Well, that's where we use the fact that there's no sparse set. So basically, if I take a K2n 2n and kind of do, look at some paths coming off of a vertex, if those paths are very unlikely to have an edge between their endpoints, you can sort of use that information to build a large sparse set. Okay, that's a very high-level vague intuition, but that's kind of the idea. So if one of your graphs is not quasi-random, you can use that to find and use the fact that there's no sparse set to construct a lot of copies of the graph that we want. So now imagine that every single one of these GIs is fairly quasi-random. So the number of 4 cycles is sort of close to what it would be in a random graph. This turns out to be kind of the trickiest case to deal with, perhaps. So we have to resort to some kind of spectral arguments. So if the graph is quasi-random, another way to say that, apart from talking about 4 cycles, is that there's a large spectral gap in the spectrum of the adjacency matrix. So the second largest eigenvalue in absolute value is a lot smaller than the biggest one. And the eigenvalues of the adjacency matrix sort of control how many cycles you have of any given length and kind of how they're distributed in the graph in some sense. So this is kind of, again, the vague high-level intuition. The details here are a little bit messy, but sort of using the fact that you have this large spectral gap, you can get a lot of copies of this graph, which is kind of the building block of our graph. So K22C5, because you basically should see a lot of 5 cycles and 4 cycles kind of evenly distributed, and kind of the fact that 4 cycles depend on the 4th power of the eigenvalues, and the eigenvalues are all small except for the main one, and the 5 cycles can depend on the 5th power. This kind of works in our favor. And also then you can get lots of copies of this graph, which is what you get from, or you could glue as many of these kind of 4 cycles as you want, and that turns out to be useful. And then you can get lots of copies of our graph by doing some more Cauchy-Schwarz. Okay, yeah, sorry that all of these details are a bit vague, but trust me, it's not terrible, but you don't want to see me go through these calculations in a talk, basically. Okay, so let me now mention a few other results from our paper. So this was not our only result. So we also prove a few things about, well, so this addresses what Jan asked earlier. So Jan asked, can there be a graph which is K common for all K, but which is not bipartite? So that's actually, yeah, so there cannot be. And in fact, what we prove is that a graph, so if you have a graph H which is K common for every K, then it must be bipartite, first of all. But moreover, it must satisfy Sidorenko's conjecture. And just to make this clear, we prove this regardless of whether Sidorenko's conjecture is true or false. So if it happens to be that Sidorenko's conjecture is false and there's a counterexample, then for that counterexample, there will exist a K for which it's not K common. Now, a second result that I want to mention, although I'm not going to perhaps give you all the required definitions because it's a little bit technical, but we also characterize graphs which satisfy a certain local version of the k-common property for any fixed k at least 3. So what is a local version? So roughly, this local version says that if you have a coloring of the complete graph where every color class is sort of, you know, quasi-random, or it's sort of close to a random coloring within some kind of tolerance, then you get the right number of copies of the graph. Okay, and it turns out, so for any k at least 3, the graphs which satisfy this local k-common property are precisely graphs where the girth is even. So the length of the shortest cycle is even. Remember, this actually connects back to what I was saying about the graph we were dealing with. So it was important that the girth of our graph was even, otherwise this would refute the commonness of that graph. And I should mention that this characterization completely matches with the characterization of locally Sidorenko graphs of Fox and Wei. Actually, we use their result. So this is from a paper which I believe is also not quite on arXiv yet. So we actually use their result to prove one direction of our result. So the fact that graphs of even girth are locally Sidorenko implies that they're locally k-common by the same convexity argument you saw earlier. But so what we have to prove is the other direction. And in particular, so this implies that, so if your girth is, if you have a triangle, your girth must be odd, right? So this implies a strengthening of the result of Cummings and Young. So we prove that, so it implies that any graph with a triangle must fail to be locally 3 common, which is stronger than failing to be locally common, or sorry, not, which is stronger than saying that it's not 3 common. Okay, so with that, I think I will conclude. Maybe I'll just mention a few open problems. So as I mentioned, kind of the most kind of intriguing problem, well, in my opinion in this area, is to understand, can we have complicated 2 common graphs or k-common graphs, where one way of measuring how complicated a graph is can it have high chromatic number? So that for 2 common graphs that was asked by Hatami, Hladky, Kráľ, Norin, and Razborov. And so we asked the analogous question, which is sort of an obvious question for k at least 3. This connects to Alexi's question. So can you find a graph which is bipartite, oops, sorry, which is bipartite, and for which you can prove that it's 2 common, but we don't know if it satisfies Sidorenko's conjecture? That's quite an interesting question. So the smallest graph which we don't know satisfies Sidorenko's conjecture, for example, is k55 minus a 10 cycle. Is that graph 2 common? And can you prove that independently of Sidorenko's conjecture? This is a question that I'm stealing from Junkyung's talk. Can you, if you have these complete tripartite graphs, are they all, sorry, I wrote common here. What I mean is 2 common. And then another question is to characterize these locally 2 common graphs. So we characterize locally 3 common, 4 common, 5 common, etc., off to infinity. But our characterization, interestingly, doesn't work for 2 common graphs, for locally 2 common graphs. So that's a quite an interesting question, I think. Okay, so with that, I'll stop. So thank you for your attention, and thanks again to the organizers for the invitation.
Thank you, John, for the talk. Could I ask everyone to unmute themselves for a round of applause for the speaker? So are there any questions to? And please either unmute yourself, or if you have a problem with your audio, just ask them in the chat and I will read them.
I can also see the chat.
Mm-hmm. Yeah. So would it be sensible to ask or something like a common pair, right? So you are doing a red triangle versus a blue triangle. Now I want, you know, a red triangle versus a blue C4.
Yeah, that does seem like an interesting question. I'm not sure if anyone has done that. One thing you have to get completely straight is how you're measuring, like, I mean, are you just going to add the homomorphism density of triangle plus C4 and you want to minimize that? Or is it some other function of these two densities that, because kind of the number of the triangle density you would think is like, if your edge density is P, is going to be P cubed, whereas your C4 density.
Right. Okay, so let's make,
really.
to stay on the safe side, let's keep the number of edges the same.
Yeah. Yeah, it's I've never seen this kind of concept, but I think it would be very interesting, right? People look at off-diagonal Ramsey numbers, right, and things like that. So it's a very natural question, but I haven't seen it anywhere.
Mm-hmm. Yeah, another problem that occurs, or well, possible question, like I spent 3 seconds thinking about it, but so could you do that for permutations, right? So you would, I'm actually not even sure for an increasing permutation of length, right? So you have a permutation and you're looking at the density of an increasing permutation of length 4 plus the density of the decreasing permutation of length 4. Right? So,
I think maybe, I think there's a paper on this, maybe with including the other Jan Volec. Did you not prove something about actually exactly that, increasing and or plus decreasing permutations of length 4, minimizing the number or something? Or maybe it's maximizing, I don't know.
No, yeah.
But
hello?
I think, yeah, we can hear you.
Yeah, it is known, and it's 1/27. And the construction is basically you either arrange 3 increasing layers, I mean 3 increasing permutations in decreasing fashion, or the converse. Or like, I mean, think of permutation graphs being either 3 cliques or the complete 3-partite graph. And the conjecture is this holds for every K. And I mean, the paper is on the 1/27 for, I mean, for the cliques of size 4. And I think the techniques give it also maybe for K equals 5, but we didn't put effort to figure out the details.
But then, so yeah, so then in general, there's a conjecture, but not a proof. But also,
okay, and also when you allow the K to grow with respect to N, then you are in sort of this R-sec-R- lemma. There is a paper of Benny and Wojtek Samoty that, like, if on the other hand, K is very close to square root of N, which is sort of the R-sec-R threshold, then it's also true. The best you get is whatever this number is telling you, whatever this construction is telling you.
I see. Okay, so then it's not minimized by any sort of random permutation then, but
not at all.
Well, but yes, so but still, I think that would be like saying that K4 is not not too common. So then I would ask, okay, I have some other funny permutation of order 5, and I want to look at that permutation and its inverse, and you know, sum up the densities.
Yeah. Unfortunately, you're going to have to.
I mean, it is known that if I think it's a recent result of a student of Dan Kráľ, that if you have 3 fixed densities of patterns in permutations, they don't imply quasi-randomness. Even knowing the number, not just their sum.
So if you
for any 3, and they even don't need to have the same order.
Right. Oh, I see. Okay, they can.
I mean, to be more precise, I believe for you give me 3 fixed patterns in permutation, tau 1, tau 2, tau 3. You can find a small perturbation of the random permuton of the random permutation, where that will keep those 3 patterns to be the same.
I see. So it's even in a local sense, you can kill the pattern, or those any 3 patterns.
But I mean, oh, no. I mean, okay, Jan, if you want to just minimize, then I mean, the answer is 0 as long as it doesn't contain the monotone increasing.
Yeah, I was going to say that you need to include both the monotone increasing and decreasing, and then maybe you can include some others, and maybe then, yeah. But yeah, I mean, if you are adding up just densities, actually, we have a paper doing something, yeah. Characterizing quasi-randomness in that sense, yeah. Yeah, with Tim Chan, Dan Kráľ.
Are there any more questions?
Mariam Shrubsida and Yanni Pahova. But yeah, any other questions?
If not, then I suggest to switch off the recording, and if anyone wants to, stay for any informal chat, then we can stay. And